Hello everybody, today I'm going to be discussing some problems from the British Informatics Olympiad. This is the 2018 Olympiad, round 2 questions. Round 2, I'm going to be going through round 2, which is slightly harder than round 1. So yeah, there are 4 problems and they require a bit more thought than round 1. So I'm going to be discussing each one, and first I'm going to explain the problem. I'm not going to read the statement, I'm just going to explain the problem as I interpreted it. Then I'm going to explain a solution, and then I'm going to implement it by writing it up, by coding it up. So yeah, that's the plan. Let's jump right in, starting with problem 1, I guess, Byway. So the problem is like this. You can pause and read it if you want to, but well, I suggest that you do. But the problem is that you are given a graph. It is weighted and undirected, which means the edges don't have directions, so you can travel both ways along the edges, but the edges do have weights, which means it takes a certain amount of time to travel down each edge, which is the same time for both directions. And basically you have the nodes are numbered from 1 to V. In this case they call it V, and you want to determine the shortest path from node 1 to node V, but the only catch is that you can halve the weight of exactly one edge. So every edge has an even weight, so you don't have to go into fractions or anything. So you can halve the weight of one edge, and then given that you can halve the weight of exactly one edge, they want you to find the shortest path from node 1 to node V. So yeah, consider the example. There's an edge from node 1 to node 2, 2 to 3, 3 to 4, and also from 1 to 4. So this is a kind of loop, and all the edges have weights 10 except for 1 to 4, which has weight 40. So let's draw that up. Over here. So you've got 1, 2, 3, this is quite a simple example, 4, the weight of this is 40, the weight of these are 10. So yeah, you want to get from 1 to 4, so you kind of have two options here, which is this or this. And now, well, this is actually shorter at the moment if you consider the path itself. But if you're able to halve one edge, then, well, the path itself comes out to 30 on this side and comes out to 40 on this side. So the 30 is actually shorter, but if you can halve one edge, if you halve on this side, you want to halve the biggest edge, obviously, but there's only one edge here, so you halve 40 to get 20, whereas for this 30 you halve one of the 10s and the 30 becomes 25. So you can't just take the shortest path and halve the biggest edge. That does not work. So yeah, this example shows that. So in this case you want to halve the 40 into a 20 and take just the direct edge like that. So that's the solution for this one, and yeah, all you have to do is print the number, which is the total weight of the shortest path once you've halved one edge. So the constraints are, you've got 2 to the 12 nodes at most, which is about 4,000. And 4096, and well, this value doesn't matter. The main thing is the number of edges, but they don't tell you the maximum number of edges. So assuming that you don't have multiple edges, which it probably says somewhere here, each will be given once. yeah, I'm assuming you can't have multiple edges between two nodes or self loops, which means that you can have approximately, at most, 2 to the 12 squared edges, which is not too small. It's about, I don't know, 10 to the 7, about 10 to the 7 edges. That means that you can't just brute force it. So if you wanted to brute force it, what you would do is, in whatever graph you had, you would try, by the way, if you want to solve this problem, you need to know some kind of shortest path algorithm. So I recommend Dijkstra's shortest path, which is my favorite. So if you don't know that yet, look it up, Google it. I might have an explanation in the description. So check out a video on Dijkstra's that'll help you out for this. So yeah, so say this is node 1 and this here is node V. And yeah, each edge has a weight, but it'll take a while to write them up. The brute force method, the obvious method, would be to go around trying to halve the weight of every edge. So let's say you're at this edge now. You say this edge has weight 20. Let's halve it to 10. And let's try and now find the shortest path from 1 to V. And yeah, you do that for every edge. You halve the weight of one of the edges, and you launch some kind of shortest path algorithm to find the shortest path from 1 to V. Problem with that is, for each shortest path algorithm, for Dijkstra's complexity, the complexity of Dijkstra's shortest path is O of V plus E times log V, which basically means the number of, well, where V is the set of vertices and E is the set of edges. So the size of the set of vertices, or in other words, the number of nodes, plus the number of edges times log of the number of nodes. Right here, the worst this could be is, well, the edges could be up to 10 to the 7, the nodes up to around 1,000, 4,000. So this is around 10 to the 7 times log of 1,000. So this could be around, well, let's just put it at around 10 to the 8. But this is fine if you want to do it once. But the problem is, if you go through every edge and do this, that is, well, V times this. So that could be like 1,000 times 10 to the 8, which is 10 to the 11, which is obviously not going to work. So that's too many operations. So yeah, brute force doesn't work, but there is a way around this, and that brings us to the solution. So the solution is this. Well, my solution. There might be another solution, I don't know, but this is my solution. When you have the graph, you consider every edge, and for each edge you say what is the shortest path such that you halve this edge and you use this edge as well. So let's say for any edge, let's say for this edge, we will find the weight of the shortest path which uses this edge, and where this edge is halved. So how do you do that? Well, say this edge has a weight of 22, then well, you're halving this edge, so that's 11. Okay, you've got that. Oh my god. Yeah, you've got 11 on this edge, and now you want to find the rest of the path, obviously. So how you do that is, you've got this edge now with weight 11 that you're using. You've halved the weight from 22 to 11. And now you want to connect this somehow to 1 and to V to make a path. And One way is to connect this node, this end of the edge to 1, and this end to v with some path, and the other way is to connect them the other way around, so this to 1 and this to v. And by connect I mean find a path from this node to 1 and this node to v. So yeah, you try both ways, and for example, if you want to try this edge, this node to 1, you can just take the shortest path from 1 to this node, add 11, and then add the shortest path from this node to v, and that gives you the shortest path in which you include this edge and you're halving this edge. And yeah, you're going to do that the other way around as well by finding the shortest path from this one to 1 and this one to v. And obviously the shortest path from one node to a second is the same as the shortest path from the second node to the first, because this is undirected. So that means that if we initially find the shortest path from 1 to every node and the shortest path from v to every node, then we'll be fine because we'll have everything we need. So that's the solution. You initially launch some kind of shortest path algorithm twice, once from 1, once from v, and once you've done that, then you go through every edge and try connecting it in both ways. So, well, there is a chance that this might not work because, as I said, it's around 10 to the 8 at most per shortest path, and 2 times 10 to the 8 is close to the limit, but I'm not sure with the constants of, well, priority queue, which is what you use, priority queue, which is what you use for Dijkstra. I'm not sure how that will play out, but this is the first problem, so it shouldn't be that hard, and this is the complete maximum, so if this doesn't work, I'm assuming this is probably the intended solution they're looking for, is what I'm saying. So yeah, that is the solution. Now let's implement it. So input, you're given the number of nodes initially, then you're given just lines of 3 numbers, which are this node is connected to this node and the weight of that edge is this, which, as I said, they say is always even, and -1s at the end to signify the end of the input, which isn't usually the method used. Usually you get a number which is the number of edges, but yeah, that's fine. Okay. I'm going to need algorithm as well. Okay, so we get v, they call it v, so let's stick with v, although I prefer n. We've got v. Now we're going to have a vector of vectors, and I'm pretty sure this is let me just check. Yeah, the maximum weight of an edge is 2 to the 50, which doesn't fit in integers, which is integers around 2 to the 32. So 2 to the 50, you'll need longs for that. And what is the max? If you look at the maximum total weight of a path, it's approximately 2 to the 50. Well, each edge is at most 2 to the 50. And the number of edges is at most the number of nodes, obviously, because these paths are going to be simple paths. So 2 to the 12, but 2 to the 12 times 2 to the 50 is 2 to the 62, which is quite close to 2 to the 64. So it's close to the limit of long. So I'm going to need some kind of long called LL max or something, and this is basically the biggest value that you can fit in a long, and I'm going to use it. Well, I'll show you where I'll use it, but how you create this is that. So basically what this is you take unsigned long, you take all zeros in an unsigned long. These are bits, by the way. Then you take not that, so that turns everything into a 1, including the first bit, which in a signed long would be the sign bit, but in this case it can be used as a 1. But now we want to convert it into this is the biggest value that you can fit in an unsigned long, but we want the biggest value in a signed long. So we're going to shift this down by 1 to the right. That basically turns this into a 0. And now when you cast this into a long from the unsigned long, that will be the biggest value, because the signed bit, if the signed bit is 1, that means it's negative. So we leave the signed bit as 0 and the rest are all 1s. So yeah, if you print this, it's going to be some big number. Yeah. This. Okay. And we begin. This is the adjacency list. I call it G, you can call it neighbors, anything. So for each GI is a vector of pairs of in and long. The first thing in each pair is a node, and the second thing is the weight. So this basically contains every edge leaving a node. Yeah, so we're going to need some x, y, and t. That's what they call it. And while c in x and c in y and c in t and x is not -1, so this will just do the input for us. Neighbors of x, we want to add y, t, and neighbors of y, we want to add x, t. There we go, that just does the graph. Now, I'm going to write a lambda function for shortest path, which is basically a function that you don't have outside, you have inside here, because, yeah, why not? Shortest path. Okay, so I'm going to have distance, which is the distance of every node, but well, that's a vector, but you need 2 of them because you need distance from 1 and distance from v. So how I'm going to do this is you're going to give start to the function and store. So start is which node you're starting from the Dijkstra's shortest path from, and store is which of these distance arrays you're storing in. So store is either going to be 0 or 1. Okay. So what we do initially is, well, we need to prepare some stuff. So firstly, distance is empty. The vectors themselves are empty. So we want to set distance store to vector long. Actually, we need longs. Vector long of size 1 plus v and with values long max. So that's what we need this for. So initially the distance to every node is basically infinity. This is infinity. Not literally infinity, but you know what I'm saying. So now we need q, include q, and now we need to set up a priority queue. at least I can spell it this time, of pairs. It's going to be pair long int. So basically what this is a queue where you put in this type of element. So the element will be, the first value will be the weight, the distance to the node, and the second value will be the node itself. And when the priority queue allows you to take the smallest value out of this, but well, by default the priority queue allows you to take the biggest value out that you have currently stored. So I'm going to reverse that by adding this stuff, which so this what this basically does is by default the comparator it uses is less, but I'm changing that to greater. So now every comparison it makes will be reversed, so it will basically sort it in the other way, although it doesn't actually sort it. But. So that's the priority queue. We also need one last thing, which is scene. So this is just classic Dijkstra's, by the way. I'm just going through it slightly slowly so you can kind of follow along, but you should know Dijkstra's or you're going to be quite confused. So yeah, now I'm going to push 0 start into the priority queue, which means I'm also going to have to say distance store. We take priority queue top second, which is the actual node. We don't need the wait. All we needed the wait for is to get the node, so for the sorting. So now we remove the node from the priority queue. Yeah. If cnode continue, cnode equals true. Now we go through child of gnode, and if not seen child, and yeah, we need to first calculate the new distance. So the new distance to this child through this node is distance store of node plus child first second. I've got these the wrong way around. And now if I haven't seen child, seen means that you already know the shortest distance, and d is less than strictly the current distance to child. So if we haven't actually even got a potential path to child yet, then that will be long max. So it will be less than long max. Then distance stored child is d, and pq in place. We're going to have d as the distance and child first as the node. So yeah, this is going to have to be child first. So that does the shortest path, hopefully. Now, all we need to do is call the shortest path from 1 to every node. From 1 to every node, so start and store. So start is 1, store is 0, so you store that in distance 0. And also we call it start from v and store it in 1. So distance 0 is now a vector that contains all the node's distances from node 1, and distance 1 is a vector that contains every node's distance from node v. So now all that's left is to find the shortest, well, as we explained earlier on the whiteboard. So min distance is long max. We're going to use that again. And now I'm going to go through each edge. So I'm going to go through every node and every pair which signifies an edge in the neighbors of this node. And now I'm going to well, first of all, I'm just going to name these proper things because, yeah. Wait equals p/second. And now, yeah, I would do this. Actually, yeah, why not? Because my compiler can handle it. Instead, I'm going to do this directly. So auto child wait of gnode is a neat trick. And if so we need to calculate the distance. So current distance equals well, you have to take the distance from node 1 to node. So distance from node 1 to node. Remember, distance 0 holds the distances from node 1. You need to add this weight over 2 because we're using this edge. We're halving it as well. And you need to add the distance from node child, well, we're calling it child, but it's actually the other node on this edge, to node v. And remember, distance 1 is a vector that contains the distance of everything to node v. So that should do it. That should find the current distance, and min distance equals min between current distance and min distance. And that's min is why you need algorithm up here. So yeah, that should do it. By the way, I did say in the whiteboard that I need to check both ways, so both ways to connect it. So the first node to 1 and the second node to v, and vice versa. But this code will do that because for each edge, for example, the edge between nodes, say 3 and 5, when I go through, when this loop gets to node 3, and this loop gets to node 5, so within node 3, so that will go through this edge, and it will try connecting 1 to 3 and 5 to v. But then later on, when this outer loop gets to 5 and the inner loop gets to 3, it'll try connecting it the other way around. So it may seem like I'm only connecting it one way, but in fact I'm going to go through each edge twice, both ways. So I'm going to do both ways. Oh, this child first again. Yeah, child is a pair. Child first is the actual node, child second is the weight of the edge. So let me copy this. 20. 20 is in fact the correct answer. I don't. Yeah, I guess that's it. The Olympiad organizers don't have any. Oh, the Olympiad website doesn't have any tests or anything on it. So yeah, I can't really test my code unless I write a generator for the tests and stuff, which I haven't done in this case. I have done for a couple of the other problems actually, but I haven't done here. So yeah. So that's it. That is Byway. Yeah, let's move on to the next problem. Let's move on to Best of Show. Now, Best of Show actually has a bonus version, I think. I'm pretty sure. Yeah, this is the bonus version, but we're just going to do this version right now. best of show. So the problem is, well, again, you should read the problem, but I'm going to just explain it in my own words. So let's just clear this. How should we? I'm just going to make a new one then. So you've got well, n. They're called movies in this case. N movies, which is up to 2 to the 10, which is 1024, 1024. So up to 1,000 movies. Hello, this is off. We have up to 1,000 movies. That's n. And each movie, for each pair of movies, we know which one's better. So that's around n squared comparisons. Well, n times n minus 1 over 2 comparisons. Each pair of movies we know which one's better, so that's kind of like a matrix. Of comparison, so that shows which one's better. And we want to organize these movies in some order such that each following movie is better than the previous one. So so that each film is better than the immediately preceding film in the list. That's basically what you have to do. So yeah, you want to make some kind of list, and you can consider this obviously as some kind of graph where you have an outgoing edge from, well, the nodes are all the movies, so yeah, and you have an edge, between every pair of nodes, but it's directed, so yeah, and the direction means that the edge moving from 1 to 3 means that 3 is a better movie than 1, which means that 3 can go directly after 1 in the order. And now you want to find some sort of Hamiltonian path, I guess. Hamiltonian paths are actually a NP-hard problem, so you can't actually do it in non-polynomial time, but this is different because the type of graph is fixed. It's I think it's what's called a tournament graph, which is a complete graph, so every edge is there, but then every edge is directed. So this isn't actually too hard, and how you can do it is like this. You can kind of initially start with one edge, I guess, or even one node, but one edge. So you want to find some kind of path like this where every node is included once, and you have an edge from every node to the next node. So initially, if you start with only one node, or let's just show one edge, but you can start with one node. So let's start with two nodes with an edge between them. So this is a valid path. This is a valid order of movies, where each following movie is better than the previous one. The problem is you've only got two, so that's not enough because you want all of them. Now, there is a way that you can add another movie in this. So let's take any other movie, and this movie will have either an incoming or outgoing edge from /to every node already in this list, like this. So how do we add this node into this order, into this path, into this line? Well, let's go through the line. Well, in this case, we've only got two nodes in the line. So let's check the first node. If you've got an outgoing edge to the first node, then just add this node right here before the first node. So yeah, that's it. Yeah. Otherwise, that means you've got an incoming edge from the first node. So now let's look at the second node. If you've got an outgoing edge to the second node, you can add this node between the first and second node because you've got an incoming edge from the first and an outgoing edge to the second. So you can add it in between, like this. Well, like shown here, you can just use this and use this. So you can make this order. Otherwise, that means you've got an incoming edge from both nodes. I don't want to erase everything. Otherwise, you've got an incoming edge from both nodes, which means that you've got an incoming edge from the last node, and if you've got an incoming edge from the last node, you can add it at the end. So that was just for 2 nodes, so now let's make it more general. If you've got some kind of... what is going on? If you've got some order so far, some path that is valid but doesn't contain all nodes, now you want to add another node in. Now you go through every node from left to right, and you do this. You check, you find the first node to which this node has an outgoing edge. So if that node is the first node itself, for example, you can add this node, you can add node I, let's just call it node I. So the node I is the node we're adding to the list now. If node I has an outgoing edge to the first node in the list, then you can add node I to the start of the list. Otherwise, if it has an outgoing edge to the second node in the list, you can add node I between the first and the second nodes in the list, and so on. So if you take the first node to which node I has an outgoing edge, you can add it right before that node in the list, because it must have an incoming edge from the node before, because this is the first node, which I has an outgoing edge to. That means you can add I in between like this, and that works for the first node as well. Otherwise, that means you don't have, if no such node exists, that means I has an incoming edge from every node, and in that case, it has an incoming edge from the last node as well, so you can just add it at the end. So that's it. The algorithm is quite simple. So yeah, you can just go through every node in whatever order you want, and you can start off with just one node by itself, and you can just do this. You can start off with node 1 in the list on its own, then you can look at node 2. If node 2 has an outgoing edge to node 1, you add it before, otherwise you add it after. Then you take a look at node 3, and if node 3 has an outgoing edge to any of these already in it, then you add it just before the first one it has an outgoing edge to. Otherwise, you add it on the end, and so on. You do that for every node, and that just works. So yeah, let's implement that. Now, what's the best data structure to store this? I'm going to use a list in this case because, yeah, list just sounds like, even though you might not use lists very often, list just sounds like the best thing for this. This is a list. You don't need random access. So you never need to randomly access the 8th element of the list. You can just go through them from the start, which is what we're doing. But we do also need to include vector because, yeah, we need to store the matrix and everything. So you get n, then for some reason you're not giving this in a matrix form, but that's fine. But you're giving this in the form of, you're given every pair, and for each pair the first one is the winner, So the first one was better than the second one in the pair. So yeah, for example here, you're given 1, 2 means 1 is better than 2, 2, 3 means 2 is better than 3, etc. So you're given n times n minus 1 over 2 pairs. I'm just going to do this with, you just have n, x, y. Well, let's do a matrix. Matrix of size 1 plus n, and each within is also size 1 plus n. So yeah, you've got that, and while c and x and c and y, well, I'm going to call this w and l just like they did, because w is the winner and l is the loser. So w is better than l basically. And matrix w to l is, well, we want to say that if this is false and the opposite is true, because this means that there is an outgoing edge from L to W, meaning that W is better than L, and so we can put W after L in the list, and vice versa. If you have W before L in the list, that doesn't work. Sorry, this has to be true. So if you have L before W in the list, that works. If you have W before L, directly before L in the list, that does not work. You've done that. That sets up the matrix. Now you have list of integers, order. Order, insert one. So this is node 1, we're just adding node 1 to the list. And now for I equals 2, I is at most n. This is which node we're adding. Again, it doesn't matter which node you're about to add. We're going to have found equals false. So yeah, we're just going to iterate through every element in the list using an iterator, while we've not found the element that we're placing before, that we're placing node I before, and while we haven't reached the end of the list. So what are we going to do here? We're going to check if you've got an outgoing edge. So I'm going to take the value of it, and if matrix ij, that means there's an outgoing edge from I to j, which actually in the terms of movies means that j is better than I. If this is true, that means you can put I directly before j in the list, and because we're still in the loop, that means that the film before j in the list is worse than I, so we can put I in between. Found equals true, and we're going to insert into the order this value, I, and we're going to put it before j, so we're going to put it before the iterator, and we're going to, well, put I in. And at the end, if we still haven't found anything, that means we can put it off to the end, as explained earlier, because that means it has an outgoing edge. Well, node I has an incoming edge from the last node in the list. If not found, that means, yeah, we insert before the end. So, by the way, list inserts, if you don't know how they work, is you give it an iterator as the first first element, and as the second parameter you give it the value you want to insert, and it inserts this value directly before this iterator. So in this case we're giving it order end, and that means we put it before end, but end is actually one past the last element, so we're putting it, well, at the end. That'll do it, and now at the end we can just, for an I of order, cout I, and then, you know, that's it. Best of show is having been written. Well, now I have to check if it's right, and currently it's awaiting more input. Oh, this is because of the fact that I've got this, which doesn't allow you to input by hand. This works for files, but it doesn't work here. So I'm just going to change it. I'm going to do it with a for. I0, I is at most n times n minus 1 over 2. Right. That's the number of pairs that we have. Yeah, that should fix that error. Oh, by the way, if you're completely confused as to, I forgot to explain at the beginning of the problem that, yeah, this might not be clear, that in this problem, if a movie A is considered to be, better than B, and B is considered to be better than C, that does not mean that A is better than C. So yeah, this is a different kind of problem. So that's why this problem actually, makes sense as a possibly difficult problem, because otherwise it wouldn't be as difficult. So 3214, and yeah, they say 3214 is valid for the example, and you can check yourself, because for the example 3214, is that a valid ordering? Well, we see that this pair shows that 2 is better than 3, so you can put 2 after 3. Then this pair shows that 1 is better than 2, so you can put 1 after 2, and this pair shows that 4 is better than 1, so you can put 4 after 1. So yeah, that's the answer. That's it. Now, I do have a tester for this. I wrote up a generator and a tester, so I can do that now, although I'm going to have to migrate from code blocks, which is this editor, into VS Code. So give me a second while I do that. Okay, we're in this folder, so this is this folder, this is the code that I just wrote. We're going to do prompt this, just to make this prompt a bit shorter. So yeah, this is the code. Now, oh, we are in Byway though, so we want to we're in best of show now. So now let's let's check out. I've written a generator and a tester for this. Which has actually, the tester does have some extra prints, but we'll leave it. So the generator just generates a test. So max n is 1000. That's fine, because max n is indeed 1000 in the problem. Well, it's 1024, but so this generates something random up to max n. So let's run the generator. This puts, well, the generator outputs into input.txt. So if we just run the, we need to compile the generator. Or build, as this calls it. Generator n equals 765, it's done that, and now if we open input.txt, we've got some test case in this. Nice. Now, well, I'm gonna open that on this side. Now we're going to run my code, which is best of show. We're going to give it input text, and we're going to output in answer text. So right now answer text is empty. So we're going to go and do that. Bang, it's done something. It's put them in some order. Looks kind of fishy, the order, but yeah, it's just some random order, I guess. Whatever order it made, and now we need to test it. So tester, we compile the tester. This is the tester. We build tester. And now tester. Yeah, as I said, these prints are unnecessary, but yeah. Tester is taking a while, but it said okay in the end. And yeah, well, that means the answer is right. If you, I guess, probably swap these round, just to make sure that the test is actually correct, let's swap the first two round, and that will mean that this answer will definitely be wrong, because if in this order they were correct, that means movie 763 is better than 764. So if you swap around the order, then it will definitely be wrong. So let's just run that again, and yeah, it's just wrong answer. So yeah, this was the answer it gave. I'm just going to use time it, which is some program that I made. I'll link the blog in the description, blog and Code Forces, but it lets you time a program. So I'm going to time how fast it took to do best of show, my code, and I'm going to give it file input from input text. I'm going to output, well, I'm going to leave the output here, because if I output into answer text, then it will put all the results in there as well, the time it took. Here we go, 1.19 seconds. Yeah, if you optimize the input and stuff, that might even be lower, although actually the input isn't. Yeah, the input is actually quite high here, because you've got like millions of, up to like 10 to the 6, up to 1 million possible things that you have to input, pairs. So yeah, the input is actually could be quite large, so if you optimize the input, this will go lower. So 1.19 seconds. I could even do that here. Let's see. Actually, I'm not sure what this will do, because I've got it open in code blocks as well. Do you want to reload it? Yes. Yeah, okay, that's fine. All I've done here is just, well, if I just open this, all I've done here is just added input and output optimizations. Now I'm going to rebuild. And run that again. Yeah, that took half a second. So yeah, this is, I guess, the solution. It works on this test. You can do another test. You can run generator again and do another test. But yeah, guess that's it. So that's best of show. So yeah, we've done Byway and best of show. That leaves Détente and cables, which actually I don't think are too much harder. In my opinion, Bio 2018. I don't know. Maybe it's not like other bios, but these two aren't too much harder than these two, in my opinion. Well, especially cables. Détente is probably the hardest of the lot to spot the solution. Maybe, I don't know. So yeah, let's get into those. Alright, so let's move on to the next problem. Détente, problem 3. Again, I'm going to explain the problem in my own words, but you should read it first and attempt it if you want to. So this is the problem. You have a grid, and in the grid, the size of the grid doesn't really matter. But in the grid, you have some spots, some positions in the grid where you have to place things. So yeah, this drawing tool converted this into a square, but you know, it's kind of infinite. You don't care about the size. So you have some slots where you can put things. So you have this, 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 something like that, and you need to put either A or B in each slot, one or the other. So, for example, you can put A here, A, B, A, B, A or something, but this here is invalid. So once you've put them in, you have to put them in a way that this no row has the difference between the number of A's and B's cannot be more than 1. So in this case, the difference between the number of A's and B's in this row is 2, because you have 2 A's and 0 B's. So yeah, and that applies to columns as well, rows and columns. So in this case, this is invalid because you have 2 A's and 0 B's in this row. So if you wanted to fix that, you could put 1A, 1B, A, B, A, B, something like this. This is valid. Actually, in here you have the difference as 0 for every column and every row, but for example, in this case, you'll have to make the difference in one of the positions. So here, now this row, you have 1B and 0 A's, so the difference here is 1, but that's fine because it has to be at most 1. So that's the problem. Now how do you solve it? Let me just leave this and migrate to over here. So this solution is like this. Let's consider any slot. Let's take any slot. I'm not going to draw out the whole grid. Just let's just say this is a slot that we have to put something in. Now let's say we put A in here. Let's put A in here. And now let's find any slot that's in the same row as this slot. So over here somewhere. And let's put a B in this. Now this has just cancelled out this row. So this has changed nothing in terms of the difference of A's and B's in this row, because you've added one A and one B. So the difference has remained the same. Now let's look at this B, and let's take any slot that hasn't already been filled in its column. So let's take this, and let's put an A in that. Now again, if you look at this column now, it's also cancelled out, 1A, 1B. So this row and this column have cancelled out. Now let's go again. Let's find something in the row of this new square, of this new cell, and let's put a B in there. And you keep going. So now something in the column of this, something in the row of this, something in the column of this, and nice cell. And yeah, you keep alternating A, B, A. Now what's happened? So you've traced this path, and what's happened is in this row, you've cancelled out basically everything. This row, this column, this row, this column, this row, this column, except for well, two things. You have this row, which is a problem because you've added one A and you've added no B's. Well, actually, you've got another A and B here, but that changes nothing. And this column. So you have these two kind of critical or problem-causing areas. Well, one column, one row in this case, but you could have two columns or two rows. For example, if you continued on here and found something in the same row as that and put a B in this case it wouldn't be this blue row, it would be another column. So you'd have two problematic columns. So yeah, but the thing is, if you keep going, so why don't we just not stop? So this A creates a problem in this row, but we don't stop, so we keep going. We keep looking for, okay, we're looking for another one in the same row, then another one in the same column, so on, until you get to a point where there are no more cells, there are no more slots in the same column or row, whichever one you're looking at next. There are no more slots available which haven't already been filled. Now, in that case, what can we conclude? If for this cell, let's just return to this cell as the example. So if for this cell over here, I'm not sure if you can see the cursor, so I'm going to circle it. If for this cell, you know that it potentially causes a problem in this row that it's in, because it hasn't been cancelled out. However, there are no more empty slots in this row, because otherwise you would have kept going. That means that you can just forget about the fact that this cell causes an imbalance in this row, because as there are no more empty slots in this row, this won't be a problem. So this cell will increase the number of A's compared to the number of B's, so change the difference by 1. But if we know that up until now the difference is definitely 0, then this change by 1 won't affect anything. And how do we know that the difference in this row is currently 0? Well, it's because if we've only made chains like this chain that we've just drawn out here, that means that the only time that we would have changed the difference between the number of A's and B's in a certain row or column is if there are no more empty slots available in that row or column, because otherwise we would have balanced it out and gone on. So that means the only time that we will, so the difference between A's and B's in every row and every column is always 0, unless we are going around and we're looking and we keep going and we get to this row or column and we stop because there are no other remaining empty slots in this row or column. But as we said, that means that this imbalance won't be a problem because we won't touch this row again or column. So that's the basic idea. So you'll have a bunch of these chains. So you just have to keep looking for chains. So you just go up to some random point and you go in one direction, continuing the chain. And then obviously you also have to go in the other direction, because both ends of this chain have to be at a point where the imbalance that it causes, whichever direction it causes an imbalance in, that won't be a problem because there are no more slots in that direction, in that row or in that column. So yeah, you start here, you put an A or B, doesn't matter, in there. You start in any cell, you put an A or a B in, then you go in both directions with this alternating direction thing until you run out of slots, and then yeah, you also place A's and B's alternating in these slots. That is a solution. There is one detail that I'd just like to mention, which is that if these two cells, which are at either end of this chain, if these two cells end up to be, what happens if these two cells end up in the same row or in the same column? Well, let's see. If this cell causes a problem in this direction, if the cells cause problems in different directions, so we've said that this cell causes a problem in the row direction, meaning that it causes an imbalance because there is no B to cancel it out. And we said that this cell over here causes an imbalance in this direction. So if they cause imbalances in the same directions, in different directions, so one of them horizontally, one of them vertically, as shown here, then these imbalances won't affect each other because they will never be the same row or the same column that will have an imbalance. So the imbalance will always be at most 1. But if these imbalances are in the same direction, so you have two cells which cause imbalances in the same direction, and these cells are also in the same column, like this, so they both cause an imbalance in the same column, or they're in the same row and they both cause an imbalance in that row, what happens then? So if two ends of the same chain, because we've already seen that for different chains can't affect each other, but what if two ends of the same chain cause an imbalance in the same row or column? Well, if you take a look at the chain, if two ends of the same chain cause, for example, an example of that would be if you continued on from this cell to find a cell over here, which you would put a B in, and now this B causes an imbalance in the same direction as this A. So this this cell is no longer an endpoint. This cell is now an endpoint, and it causes an imbalance in the same direction as this cell does. But as you can see, it's fine, because if this happens, the two cells that are causing an imbalance will actually have opposite letters. So one of them will have A, one of them will have B, and that won't be a problem, obviously, because instead of causing a difference of 2, they will actually cause a difference of 0. So they'll cancel out, and this will form like a big cycle instead of a chain. So yeah, that's all I wanted to mention about that. So I've mentioned why the solution is correct, but I haven't explained too in depth how you actually implement the solution. So we're going to have 2 sets, well, 2 vectors of sets, which contain, actually instead of vectors, let's take a look at the constraints. We have n up to around 1,000, well, it's actually around 10,000, and we have x and y up to 2 to the 16, right, which is about just under 10 to the 5, I think. Yeah. So if we this is quite small, so for each row, if we have a set of the cells in that row, and for each column if we have a set of the cells in that column, that will allow us to work out find, because as you remember, we need to be able to find an unused cell in the current cell's row or in the current cell's column. So these sets will assist us with that, and once we've used a cell, we'll delete it from both sets that it's in. So the set of its column and the set of its row. So we have max, what is this? Max value, just call it max value. It's the max biggest coordinate, biggest x or biggest y. So we have that as 2 to the 16, and we're going to make 2 sets. Well, we could have an array of sets instead of a vector. Could have done a vector, but yeah, an array of sets called with x and with y. So, and each one will be 1 plus max v size. So with xi is a set that contains the indices of all cells with I as their x. Yeah. So basically, with x, or you give it x, and it gives you a set of all slots that have that x. So let's set this up. Input, you just have this, yeah. We're going to have x and y. We're going to input like that. Oh, and also we need to put in the set. So with x of xi, insert I. So yeah, indices are what we're storing. Yeah, we've done that. Now we're going to make well, we have to have something that stores whether each cell has already been assigned a character or not, so that, well, also partly because we need to print that answer at the end. I'm going to store that as a string. Well, that means it's going to be of size 1 plus n, because I'm going to keep one-based indices, indexing, one-based indexing. I'm going to fill it with spaces at the start, meaning that I haven't selected an answer. Now I'm going to iterate through all the cells. So we're going through all the cells, and if we've already selected an either A or B to put in this slot, then we're going to continue. Otherwise, now what we're going to do in here is go in both directions and do this kind of orthogonal search, as we did from A. We only showed a search in one direction, but as we said, we're going to go in both directions. How are we going to do that? Well, let's have an inline function that searches in a direction. Let's call it go from, and that receives a starting node or a start node, and it receives, well, it doesn't really need start node because, okay, let's just give it start node, and direction. And it will now go in this direction. So all we need to call here is go from start in direction 0, let's call it, and direction 1. So these are the two directions. One of them's x, one of them's y. So now we're going to do the actual, well, iteration. While we don't actually need start node, so let's just call it node, and while node is not -1, so if we set node to -1, that means there's no more space. There's no more. There aren't any available slots in the row or column of the previous cell that we filled. So what are we going to do here? We're going to find the next node. Now let's say we have that in some variable called fol. That's the following node. Now I'm going to leave that bit out for now. Then I'm going to set answer fol to answer A plus B minus answer node. So whichever one answer node is, this will set it to the other one out of character A and character B. Remember, we can add these and subtract because they are actually, well, characters are actually numbers. They're character codes. They're represented by their character codes. And now we can set node to following. And we can reverse the direction. The direction is either 0 or 1, which represents whether we're going in the X or Y direction. So now we've got find the next node. I'm going to leave that comment actually. And now we're going to find the next node. So how do we do that? Okay, so if the direction is equal to 0, then let's find a node in the same row. Or it doesn't really matter. So following equals if with x of node empty, this is a set so it does have empty, then following equals -1, otherwise following equals with x node begin, and same for the other direction but for y. So if with y of node, so if empty means that nobody has the same y, then following equals -1, otherwise, well, no empty slot, otherwise we set it to, well, begin because any, you can choose any, and you need that. I forgot about that. The only problem right now is that we're not erasing the current node from its row and column, and that means that this empty will actually never return false. This set will never be empty because we haven't erased it from its own set, so it will be in this set. So actually following might be set to node itself. So we're going to fix that by erasing it beforehand from these sets. So we're going to have with x node erase node, and with y of node erase node, those two, and now, well, I think this should work. The only thing is, what's the problem? It's not captured. We're going to have to capture. Forgot about that. Go from start 0. We forgot to do this. Happens sometimes. Okay, the only problem right now is that the only potential problem is that these erases, well, for every node, this erase will only happen once because we'll only reach it once. The only exception being start itself, because we launch go from start multiple times, twice, meaning that both times it will try to erase it from these sets. But that's fine because erase does deal with that. I think erase actually returns the number of elements erased. So let's just do S. Yeah, it prints the number of elements erased. So yeah, it said that the number of elements erased was 1 when I tried to erase 3 and 0 when I tried to erase 5, because 5 isn't there, and it's 1 for 3 because although I tried to add 3 multiple times, obviously a set has all elements distinct, so it only adds it once. So that should work. Let's test it out on the sample. Let's actually check out the sample first to see what it is. We have 0, 0, 0, 10, 10, 0, and 0, 20. I'm going to draw it here. Let's just pretend this is the grid. We have 0, 0 as one slot, 0, 10, 10, 0, and 0, 20. Yeah, 0, 20. So you have this as the example. In this case, well, you can't really go too wrong here, other than, well, these have to be different, and one of these 3 can't all be the same. So yeah, let's see what our program prints. Oh, we haven't actually written the bit where it's printing stuff. So let's copy and paste this input. That gives some sort of error. Position is at most size failed. Let's check out what it is. That could be this, although I'm not sure about that. With x, x of node, with y, y of node. I've seen the problem. So here, if we set following to -1, yeah, I forgot to, yeah, that's a bit of a mistake, but once we've set following to -1, we try to set answer following to something. So these are fine, node equals following, because node equal, so if we take this out for a second, we set node to following, which this direction change doesn't matter because when we try to re-enter the loop, node will be -1 in these cases, so it'll just kick us out. But this is a problem because if following is -1, this shouldn't happen. So if following isn't -1, we'll just do that in this case. That looks like the error that it could have been, the one that we were given. CC. Well, the spaces mean that it probably wasn't reached, and the C's aren't capital A or capital B, so yeah. First we have to set answer start to A, or anything, A or B, not anything. Yeah, I've missed a couple of points out there, but quick fixes in general. So yeah, now it does print something, A, B, B, A, A, So it's put A, B, B, A. Let me just, yeah, you can't see it too well, but I actually colour them different colours. A is red, B is blue. Should have thought of this before. So yeah, this is obviously fine because for this row we have A is greater than 1, A is greater than B by 1. For this row we have B is greater by 1. For this row we have equal. And then for this column we have red is greater by 1 and blue for this one. Now that's, well, how would it have found the chains here? Probably did something like this. So started here because this is the first node. So it would have gone here in this direction, or here, probably here, yeah, here because this has lower index. It would have gone here in this direction, then it would have stopped, so it would have found this chain. It put A here and B's here. That stopped. These are the dangerous directions. And then these were already used, so it skipped them, and then it got to here and it couldn't find anything in either direction. So yeah, that's how it did it. And as you can see, it produced the correct answer. I do have a tester for this, so we're going to open VS Code. For some reason, it's made this big again. This is just getting in the way, so I'm just going to change the prompt just to be this. This is smaller, so it's just more compact. Yeah, we're going to leave best of show because we were in that folder and go to Détente. And yeah, we're going to close all these. Let's open the code. This is the code we just wrote. And we have the generator and the tester. And these files, which are meant to hold the answer and the input. So yeah, well, this should already be compiled, but actually, yeah, that should already be compiled, and I think VS for some reason doesn't allow, doesn't like lambda functions, so I'm not going to compile it again, but I'm going to compile these because these haven't been compiled. So the generator, let's try it. It's just created this test. So there are 710 points. It's got max n as 10,000, which is approximately, as I said, approximately the maximum number of nodes. 710. So tester, now we're gonna compile the tester. Well, first let's run my code by giving it input and writing it to answer, which is this file over here, which is currently empty. But now it's written this. If we time that using that program again, I've put it in, yeah, I'll just leave it here because I don't want to write the execution time in the file. But yeah, as you can see, this is quite quick, 0.06 seconds. I'm gonna do this again just so we don't have the execution time in the answer file. But now I'm gonna compile the tester. And build finish with warnings. Warnings, I'm not sure if that's a problem, so I'm going to try it, but if it doesn't work, then I'm going to change these from auto to pairs. So yeah. I'm going to try testing it though. Tester. It says okay. So yeah, that should work. If I just change this, I'm not sure if that'll, yeah. So I just changed the first 6 characters from A's to B's, and yeah. So as you can see, that did it. So yeah, I can even get another test. I can generate it, and it's 762. Then I can run, and then I can test. I said okay. So yeah, you can do that as much as you want. Yeah, so I guess that's, I'm going to assume that's correct once again. Yeah, so let's say that's correct. There is actually another solution for this, which I'm going to briefly mention, but I'm not going to implement. I'm not going to code it up. But there is another solution that is quite interesting. So I'm going to mention it. And this involves representing, well, it's actually, yeah, this involves representing this grid as a graph, which is actually used often in problems. Well, yeah, relatively often. And yeah, so it's the idea of representing the grid as a bipartite graph where you have a node for each row and you have a node for each column. So you might have row 1, 2, 3, 4, and 6 with things in them, and 2, 3, 4, columns 2, 3, 4, and 5 that are filled. So now you can just connect. So this edge means that if a row is connected to a column, that means that there is a slot that we have to fill in that row and that column. So that's what an edge means. So an edge is basically a slot. And so you can connect them as they are. So something like this. Something like that. And yeah, now how do you solve this? Well, if you take a look at the let's just add this here and this here. Yeah, if you take a look at how many outgoing edges there are from each node, this one has 2, this one has 3, this one has 3, this one has 1, this one has 1. This one has 3, this one has 4, that's a fourth, this one has 2, this one has 1. Now, because the fact that these all sum to the same number, because this is a bipartite graph, so you can't connect a row to another row or a column to another column, that means that, well, these numbers on each side sum to the same thing, which in this case is 10. That means that there need to be the same number of odd values on each side. So there are 2 odd values on this side. Sorry, not the same number. Same parity of odd values. And there are 4 odd values on this side. And both of them are even. In another case, both of them could be odd. But it can't be that one of them's even and the other one is odd. Because otherwise their sum, the total of these, would be couldn't be the same. The parities would be different. It's quite simple to prove. So once you know that, you can say, well, why don't we connect these up? So now you have an even number of nodes in total. That means with an odd parity, with an odd degree. Degree means how many edges you have coming out of you. So you have an even number in total because you either have even on both sides, which sum to even, or odd on both sides, which sum to odd. So in total you have an even number of nodes with an odd number of edges coming off. That means if you pair up those nodes, that even number of nodes, and if you draw an edge between each pair, so it's like a fake edge. It doesn't actually exist because there isn't any. It doesn't actually exist. So, for example, in this case, we have these 6 nodes. So let's pair them up like this. Let's pair these 2 up. Let's pair these 2 up. These 2 doesn't really matter. I'm just going to shift that up so it's from the top. And these 2. So you have an even number of pairs, an even number of nodes, so you can pair them up, split them in half, pair them up. And once you've done that, now this graph is no longer bipartite because, as you can see, you've paired a row to a row, for example. So in that way, this graph is kind of meaningless now. The new edges that you've added are meaningless. But what you have done is made the degree of each node even. What that means is there exists a Eulerian path, an Euler path, which is just a path which starts from one of these nodes and goes through all the edges without repeating any edges, but so that it goes through every edge once exactly. And so there exists such a path, that means, because the degree of every node is even. Well, there doesn't strictly always exist one path. For example, if you had 7, 8, 7 something, yeah, it doesn't matter. If you had these connected over here, and if you had something like this, then this is another completely different component. So you can't find one path through both of these, but for each connected component, so in this case we have 2, we have this one, and this one. If for each component, if you find an Euler path that goes through that component and completely covers that component, then what you can do is on that Euler path, so that path will be a list of these edges in some order, you can alternate A's and B's on that path. So, for example, if you start here, you go here, that's an A, then you go here, that's B, then you go here, that's C, that's A, and then so you keep alternating what you're putting on these edges, and remember the edges are actually the slots in the grid. If you do that, then eventually each node will have the same number of A's and B's on the edges coming out of it. And why is that? Because, well, every time you come into this node, you'll number that edge. Every time you enter this node on the path, you'll number the edge that you enter with either A or B. But then straight after that, you'll leave this node and you'll number that with the opposite. So those will cancel out. And the only edge cases here are if you start in this node. But if you start in this node, then the first edge, because every node has an even degree, if you start in this node, you'll have to end in this node as well. So if you start in this node, whatever you number the first edge that you leave with, either A or B, the last edge, which you'll enter this node with and finish, will be the opposite of that, because there are an even number of nodes, so the first edge will have an opposite value to the last, because you're alternating. So those will cancel out as well. So everything cancels out. So yeah, the path doesn't actually matter anymore. All you care about now is what you've numbered the edges with, what letters you've put on each edge, because the edges are the slots. And now for each node, you find an Eulerian path in every component. And now for each node, its edges are numbered with A's and B's, so that the number of A's and B's are equal. And now if you erase the fake edges, each node only has at most one fake edge coming off of it. Because of how we made the fake edges, we paired up and connected all the nodes with odd degrees, but we only added one fake edge to each node at most. So if we erase this fake edge, then this node will be left with, because this node will be left with what we want, what the statement asks for. The number of A's and B's coming off of it will be at most 1. The difference will be at most 1. Because the difference was 0, and now you've changed the difference by 1 if you erased an edge, a fake edge. So that will either become -1 or 1. The sign difference will become -1 or 1. So the difference will be 1. If you added a fake edge, the difference will now be 1 because you erased it again. And if there was no fake edge, then the difference will now be 0. So yeah, that's an alternative solution. It uses the algorithm to find an Euler path, in this case in an undirected graph with every node having an even degree. So yeah, that's an alternative solution to Détente. I just wanted to mention it because it's quite nice. And yeah, so that's the end of Détente. Let's move on to the final problem, cables. So in this problem, you have some points on a plane. You have some points. In the example, you have 8 points, as shown here, and you have to connect them up in some loops. So here you have 2 loops, each loop has 4 points. You have to connect them up into L loops, each of size S, so each with S points. There are S times L points in total. So that no edges overlap, basically. No segments overlap with each other. So this line, no lines within a loop overlap with each other, and also no lines between 2 loops overlap with each other. That's basically the problem. All right, let's think about that. So you are also given the final part of the statement is that no 3 points lie on a straight line like this. So this is not really valid. So no 3 points lie on a straight line. Wow, it's difficult to draw it so that no 3 points lie on a straight line. So you know that much. This is impossible. So now you want to connect these up. So you have S times L points, and you want to connect them up into L loops, each of size S. So yeah, the main problem is that they're going to overlap. So we can kind of divide this up into two separate problems. So the first step is choosing which points go together in a loop. So you might, for example, as the example does, select these 4 points to go in one loop and these 4 points to go in another. In this case, the size of each loop is 4 and the number of loops is 2. So let's divide the problem up into the first step of selecting which points go in which loops and the second step of actually connecting the points for each loop. Now, obviously when you're considering the second step, you have to make sure that when you're connecting the points within loops, the lines between loops don't overlap. But the way we will do the first part, that actually won't be a problem. So initially, let's sort these points to solve the first part of the problem. Let's sort these points by X and then by Y. So we're going to sort the points by X and then by Y. So let me just redraw the points over here. Doesn't have to be exactly the same set of points, just some points. Let's sort the points by X and then by Y. So let's say this is directly above this. So in this case, we will take the points with the smallest X first, so the ones on this side, and then the points, if they have the same X, the points with the smallest Y. So we'll basically have this one first, 2, 3, 4, 5, 6, 7, 8. And now let's consider taking, in this order, the first S points, because we want S points in one loop. So let's take the first S points. Those are 1, 2, 3, 4 in this case. Now, once we've taken these points, each one of the points that we've taken is either strictly to the left of the points, every point that we haven't taken, or below it with the same X. So same X but smaller Y, because that's how we sorted it. And we know that all the points are distinct. So yeah, each point that we've selected will be to the left of each point that we didn't select, or it will have the same X but it will be lower down, like this. What this means is that let's say we connect up any pair of points that we've selected and any pair of points that we haven't selected. These lines cannot overlap, basically. These lines will not overlap. because every point on this line will be to the left of every point on this line, or sometimes in the case of this line, for example, it will be lower down, but it'll have the same x, but it will be lower. So in short, these lines cannot overlap. So if we sort the points like this and take the first L points, the first S points to form one loop, then the next L points to form the second loop, and so on. Well, in this case, there is no so on, but so on. Then what will happen is whatever lines you draw here, whatever order you connect them in, they won't overlap with the lines in the other loops. So that's kind of the first part of the problem solved. None of these lines will overlap with any of these lines. So that's the first part of the problem solved. You sort it by smallest x and then smallest y. So sort by x in increasing order and by y in increasing order. And then take chunks. So take the first s, then the next s, and so on. And that's quite a simple way to make sure that you divide these points into loops where no lines overlap between loops. Now, the second part of the problem is, well, we can forget all the other loops now, so we can do each loop individually. So now we've got a group of points that we want to sort, basically, in an order, so that if you connect them up in that order, the lines don't overlap. So how do we do that? Well, yeah, we have to sort the points again, basically, but sort them differently this time. And let's see how we can sort them. One way to sort them is by angle to a pivot. So what do I mean? What I mean is, let's take some point, some other point, any point really, and call it P, and that stands for pivot. Basically, this is the pivot. That's the pivot. I mean, pivot's just a name I selected for it, but yeah, it kind of makes sense. So this is the pivot, and now we're going to sort these points, by their angle that they make to this pivot. So you can call this altitude angle. So basically, let's take this point. What is its altitude angle to this pivot? If we draw in this, let's draw in the horizontal. This here is the altitude angle. This angle. It's a signed angle. So I don't know, it might be pi over 4. For example, which is the same as 45 degrees. This is some angle. This is the angle, so that's pi over 4, and we can sort the points by these angles. So this is the horizontal. So the reason it's called altitude angle, is because you can imagine this as the horizon, and then the pivot as U, and then this as the sun. And so this is kind of like the altitude angle of the sun. So yeah, this is if we sort the points by altitude angle, well, if we want to sort the points by altitude angle, first we have to kind of specify what the angle is slightly further, because, for example, if we take the example that we had earlier of this angle being pi over 4, pi over 4 in terms of this angle is the same as 2 pi plus pi over 4 plus pi over 4, and it's also the same as 4 pi plus pi over 4, because 2 pi basically is the whole circle, so 360 degrees if you like. So if you add 2 pi, it will still be essentially the same angle. So what we, and the other way as well, so minus 2 pi plus pi over 4. So what we want is to specify one of these, because you can't sort them otherwise, because sorting needs a specific value. So well, in this case we'll take this one, but we want to take the one basically in this range from minus pi to pi, inclusive on this side, exclusive on this side. So yeah, well, pi is this, and minus pi is kind of this. Minus pi is the same as pi, so that's why we exclude minus pi and we include pi. So, okay, we can sort these points now by their altitude angle. So this point will have this angle, which is the same as this, but since we chose the range to be minus pi to pi, it will be minus something here. So I don't know, maybe this is minus pi over 4. So yeah, once we've sorted these points, we want to choose the pivot first before we do anything. Pivot doesn't really matter, but let's just choose for simplicity. For simplicity, let's just choose the leftmost point, and this will help as well. This choice will help. So when we have the points, let's choose one of the points themselves. It doesn't have to be one of the points themselves, but let's choose the leftmost point that we have. And if there are multiple, let's just choose the lowest, because that's how we've already got the points sorted initially in part 1. So we'll just use that sorting and just choose this one, the leftmost point, and of those we choose the lowest as the pivot. So this is now the pivot. Now we want to sort these points, the remaining points, by altitude angle from this pivot. Now we obviously have to sort this point itself as well, but the angle isn't really defined from the pivot to itself. So the altitude angle isn't defined basically from a point to itself, so from the pivot to itself. So we're going to just put this point at the start. It doesn't actually matter where you put this point, but we're going to put it at the start. So yeah, we can sort these points by altitude angle. So you'll have this point first because that we just chose to put it at the start, doesn't really matter. Then you have this point because it has the smallest altitude angle, which is, well, let's add some points down here as well, so we have a better example. We've got this point first, then this point, because it's got the smallest altitude angle. Then this point has the next smallest altitude angle, so we'll choose that next in the order of how we connect the points. Then this point has the next smallest. Then, well, these two in this case have the same angle. Well, it looks like it, but let's just say this one has, let's move this point, because this won't actually happen in this problem, because we are told that no 3 points lie on the same line, and because the pivot's one of the points themselves, then this won't happen. But if it did happen, an easy solution would be to sort them first by the angle and then by the distance to the pivot, because yeah, you could just go with this one first, then this one, angle then distance. But we're not doing that because we're told that no 3 points lie on the same line, so that's just extra. So let's move this point here. So now it'll be this point, then this point, then this point, then this point, then this point. So yeah, this is what we'll make. Yeah, this always works. Now, how do you calculate the altitude angle of a point from the pivot? Let's look at that. So this is the pivot. This is some point. And we want to calculate the angle. How do we do that? Well, one way is to use, well, okay, my mouse is disconnecting my pointer. One way is to use arctangent. So yeah, arctangent, you basically, you give it the tangent and it gives you the angle. But in this case, we'll have to add some logic to that because that won't always give us what we want, as in it won't always work. So for example, for this case, we could take, well, we know that tangent is, tangent of the angle is this. So here, this is delta y, and this is delta x. So in this case, we can just, what tangent, well, if you want to use arctangent, you have to divide delta y by delta x and give that to the function. But problem with that is, firstly, well, the logic you have to add. Firstly, delta x cannot be 0. So if delta x is 0, then you don't want to call this, that'll throw an error. Well, not even call, you don't want to divide this. So instead of dividing, you have to check first if delta x is 0, and if it is, then you have to work out which of these two angles it is, by looking at the sign of delta y. So if delta y is positive, then the angle is pi over 2, which is this angle. And if delta y is negative, then the angle is minus pi over 2. So you have to do that bit manually. And also, just from the tangent, just from this division, just from delta y over delta x, you cannot really tell which quadrant the angle is in. So if you consider this, over here, the tangent is positive. Over here, the tangent is also positive, and here it's negative. But in these quadrants. But so yeah, you can obviously tell this quadrant apart from this quadrant, for example. But if delta y over delta x is positive, you can't actually tell which of these two quadrants it's in. Or if it's negative, you can't tell which of these two quadrants it's in. So you want to, if you know delta y and delta x themselves, then you can obviously do that. So what you have to add is, once you've calculated this, as long as delta x isn't 0, once you've calculated the arctangent, if if delta x is negative, so it's in arctangent gives you values in the range minus pi over 2 to pi over 2. So it gives you an angle between this and this. So what you want to do is, if the angle is in one of these two quadrants, you want to actually, well, take the correct angle. So in these two quadrants, delta x is negative. In these two quadrants, delta x is negative. So you want to, if delta x is negative, you want to add, well, you want to add pi to your angle, which is 180. So basically, if this is the actual angle, then the arctangent function will give you this angle. And so if delta x is negative, you want to add 180 to get this angle. So yeah, this angle. This one. So yeah, that's the logic that you need. You need to do arctangent, but you need to add some logic. So you need delta x is 0 case and adding pi that case as well. That's what you need to do, but there is actually a function in C++ that does this for you. So you can kind of use that. You can easily use that. It's called Détente. Let me just erase some of this stuff because it's kind of getting in the way. So Détente is a function, and you directly just give it delta y and delta x, and it does all that for you. So it's kind of similar to tangent. But it does all this for you. So if delta x is 0, that doesn't cause a problem. It works out the angle for you from the sine of delta y, as we discussed, and it also gives you the angle in the correct quadrant, and that gives you angles in this range. Where is it? In this range that we wanted. So yeah, this range, which is the full circle. So Détente, you can just use that, and it's great. And the only time it'll give you an error, if both of these are 0. And well, you shouldn't actually call this when both of these are 0. And we discussed that we can put the point at the start. Both of these are 0 means the point is actually the same as the pivot, so we can just put it at the start. So we're not going to actually call this Détente. So yeah, that's another option. In reality, because we're taking the pivot as the leftmost point, the angles will actually only be in this range, minus in this range, although you can actually have pi over 2 itself, because we've taken the leftmost point and then the lowest point of those. The angles will actually only be in this range, pi over 2, minus pi over 2 to pi over 2, although inclusive this time. So you can have points above the pivot. That means that you wouldn't have actually needed all the logic that we discussed for Détente, arctangent. All you would have needed is if if x is 0, you would have just said return. So if x is 0, the angle is going to be 90 or pi over 2. And that's all you really need to discuss. All you need to really add, but Détente does it all. Détente 2 does it all for you, so why not just use it? And because of this, we could have also done it by sorted by tangent itself. So sorted by delta y over delta x. Because in this range, or no, in this range, tangent is strictly increasing in this range. So we can just sort them by tangent instead of sorting by angle. And tangent is just delta y over delta x. So we could have sorted by delta y over delta x, which would probably run faster. But yeah, we would have similarly had to deal with the case where delta x is 0. So that would have probably been that's probably a simpler way to do it. But when I implement it, I'm probably going to use Détente 2. Well, not simpler, another way to do it. So there are many ways to do this. So let's return wherever we were to the problem. So yeah, we take the pivot as the leftmost and then the lowest point. We sort all the other points by their altitude angle to the pivot, and we print them. That's just it, because they just want you to print it in that order. So all we have to do is just sort them in that order and print them. That's it. Let's get to it. I seem to have closed code blocks. So let's give that a moment. Alrighty, then let's begin. Let me zoom in. So we're going to need some vectors. This for sorting, and CMath for arctangent. Well, Détente 2. So first thing we get in the input is S and L. So let's take those. Now we're going to have a vector of size S times L. A vector of size S times L, which needs to just call it P. These are the points. Although we can't really have vector of int, we want vector of point. So let's make a structure. Int x, y, and I'm actually going to have an index here as well. This is unusual for a point structure, but all we need this for is to print the indices at the end. So yeah, that's all I need it for. So I'm going to have, well, I'm I'm pretty sure we don't need a default construct. We can just use the default constructors rather than writing them ourselves. So now I'm going to iterate through this, and well, we have we have input pi first, and well, pi x and pi y, and then pi I equals I plus 1. So 1-based indices, these are just this is just the index so that we can print it at the end. This is the x and the y of the point. So we've done the input. Now we sort the points by x and then by y. So sort p begin, p end, and then we give it a function. The reason I'm not putting the function in the structure itself, so the operator, the less than operator, is that later on we're going to have to sort another vector of points, which is the loop itself, with another operator. So I'm just going to pass the two different operators separately. So we have point P1, point P2. This is just a simple comparison. So return pair P1x, P1y is less than P2x, P2y. So this is the less than operator. P1x, P1y is less than P2x, P2y. So yeah, this will just compare x first and then y, if the x's are equal. That's done the sorting. Now we go through the number of loops, and now we just do each loop. So vector point loop of size s. Now we're going to iterate through the values of the loop, and well, we're going to first copy the points over. So loop j equals point s times I plus j, right? Loop j is point s times I plus j, and then yeah, so now we've got the points. Now we need to sort them. So let me just take the pivot as well. As we said, we want to make the pivot the first point in the loop, which is the leftmost and the lowest, and then the lowest. That's the first point currently in the loop because that's how we have it sorted. So that's going to be loop 0. And yeah, now we're going to iterate through. Now we're going to sort using the pivot, using the angle, the altitude angle. Loop begin, loop end, and this. So we need to take a pivot in the capture. Actually, let me check. I think my face is getting in the way of this. My camera. Well, nearly, but I'm gonna move it up anyway. Yeah, let me. If I just add this, that should be fine now. Yeah, we're fine. So yeah, this is the less than operator for this sort. We need the pivot, so that's why we get in the capture. And now, well, what do? The main thing that we're going to do is return, and now we need to do a tan 2, as we mentioned. A tan 2 of p1 y minus pivot y, so this is delta y, p1x minus pivot x, this is delta x. These are for point 1, and now we need to do the same for point 2, and we have to return whether this is less than this. That's basically what we're doing. P2y and p2x. That's basically what we're doing. Now there are some cases that we need to consider. We need to consider if loop, if one of the points is the pivot itself. We said earlier that we can't call arctangent a tan 2 on the pivot because this is going to be 0, this is going to be 0, and this is going to throw an error. So we need to check both cases. If P1 is pivot, then we want to return true because pivot is less than everything. But if P2 is pivot, then we return false because pivot is less than everything, and so nothing is less than pivot. Although, if in the case that, firstly let me just write this. That's just equals operator, which we're using here. So for some reason, the point might be compared to itself. A point might be compared to itself, which should be fine unless the point's the pivot. So if for some reason the sort uses this this operator to compare the pivot to itself, then this is wrong because we want to return false. So let me just put this first, and I think that should be fine. So if they're both the pivot, we're going to return false because this will happen first. We have that sort, that's done. And now we're going to just print, they want us to print each loop, the indices in that loop, in the order that we're going to connect them. So this one's connected to this one's connected to this one's connected to this, and then this one's connected back to the first one. And then this is the second loop. So we're going to do that for this loop. We're going to for point of loop, we want to print point I. Right? It's basically what we want. That's about it. Now we just have to, well, that's wrong, first of all. Yeah, a couple of mistakes. P2 equals pivot. Yeah, I see the problem here. So this equals operator needs to guarantee that it won't change any of these. So we're going to put constant here. So this constant means that point 2 won't be changed, and this constant means that this point itself won't be changed. So I think now the equals operator shouldn't give us a problem anymore. Yeah, that runs now. So let's take the sample test case and check it out. 31458672. Let's check that out. I have the test case set up over here in it's called GeoGebra. These are the points. So let me just quickly alter this so that it prints this has letters. This website has letters instead of numbers on the points, which is fine. But we print numbers, so let me just quickly change this to print a letter instead. So we're going to print. I mean, that's the easiest way of casting it into a character, I guess. And we're going to print. Well, let's see if it works this way first. Character A minus plus this minus 1. Let's see how that works. Yeah, it prints the character code. So let me just yeah, not that. String 1 of this, basically. That's one way of doing that. Okay, now we have this as letters, so let's just take a look at what it does. Let me just quickly move this over, and now we have. So we have C connected to A, D, E in that order. So first let's check if it selected the correct points in the loop, as it should by our algorithm. So by our sorting method. So it should select C as the leftmost point, then A as the next leftmost point because it's lower than D, then D, then E because it's lower than A. E is lower than H. So C, A, D, and E should be in one loop, which they are, and these should be in another loop, which they are, the rest. So the loops are correct, or yeah, they are. Now let's connect by segments. C, A, D, E is this one, which is obviously doesn't overlap with, the edges don't overlap. And also this is how our algorithm would have sorted it. So it would have taken, how our code would have done it. It would have taken C as the pivot because the leftmost point. Then it would have taken C first because that's how we sorted it. Then it would have taken A, D, and E because they are the altitude angles are in that order. Now we do these. Second loop, H, it's taken H first, that's correct because the pivot. F, G, and B, yeah, that's the correct order. Obviously, it's the correct order as my code would have done it, so as I expect my code to do it. Obviously, this isn't the only correct way to connect up these points. As shown by the example, they've done it differently. The example shows a different way. Let's just undo all those edges and let's take another test case. So I've got these points that what in the, I want to delete these segments. Okay, so I've just added 4 points. I want to see how it deals with it. I'm pretty sure that no 3 points here are on the same line. Doesn't really matter too much for our algorithm. We could have easily adapted it so that it works for 3 points in a straight line by sorting it by angle and then by distance, as we mentioned. So let me just quickly build this test. I haven't actually built this test in Notepad, but I haven't actually built this test yet, so I'm going to build it here. So we have, let's say 4, 3, so we want 3 loops this time because there are 12 points. And we have 2, 6, 3, 7, 3, 2, and 0, 2. Yeah. Now let's run it again. There we go. Looks nice. So we have L as the new leftmost point, so it's taken that as the first pivot, so that's correct. L, A, D, C. That's nice. It's done it in the right order. Then we've got IKEJ. I is the leftmost, then K is the smallest altitude angle, E and then J, that's right, and HFGB. HFGB. That's it. So yeah, it's done these correctly. I don't have a test generator and a generator and a tester for this problem, but yeah, it seems like it's working. For these two tests. So yeah, that's it. That's my solution to cables. Yeah, sadly, as I mentioned, there are no ways to submit on the website. That would be great, obviously. But yeah, that's not vital, I guess. We can still write the code and discuss the problems. So yeah, that's it. Thank you for watching. And I'll see you in the next video. Bye.